And in this module, we are going to cover secretion and absorption, continuation from our previous lecture about diffusion and handling fields in CompuCell3D. Our objectives here are to understand how to implement secretion and uptake in CompuCell3D and start to think about modeling and things such as model structure and problem scoping before we start writing our simulation code. So to continue from our previous lecture, another exercise, very useful. This shows up very often, for example, in chemotaxis and other exercises, is how to set up a linear field. So go ahead and start from the simulation you stopped with in the last lecture, where you had a droplet, and change the initial field configuration to a linear field or constant gradient. To do that, you can just set a constant value in one of the boundaries, another constant value in the other boundary, those two different from each other, and wait long enough, you'll have your linear field. And these are some tips on how to set it up. One of the things you can do to speed up the process is to already define an initial condition that corresponds to the linear field outcome. And in your boundary conditions, please set constant value on the left side of the plane, which is the x-axis. You set constant value 1 and constant value 0 for the right boundary. With these two changes, you should have your linear field. In my initial concentration expression, I am using 1 divided by 100. 100 is because in this example, I am using a lattice that is 100, size 100 in the x dimension. If you're using some other value like 255, 256, then you do minus 1 divided by 256 instead. Or you can also set the dimensions of the lattice to 100 on the x-axis. Question from Nargis. Nargis, I'm sorry if I'm mispronouncing your name. Is there a way to add the boundary condition automatically here? So we have boundary conditions and periodic. So currently we cannot pop open that same wizard window and add it there. I already wrote the feature request on GitHub. Instead, you have to type it in, but I can give you the code for that. So there is not a built-in function for it under CC3D Python. If you are looking to change it on the XML, it's not on CC3D Python that you will find it. You will find it on CC3D ML, drop-down menu, then steppables. So if you look at my screen here, you come here, CC3D ML, steppables, and diffusions over FE. This will replace everything you have, okay? So I do not recommend you do that. I recommend you change it right here. So to change from periodic to constant value on the x-axis, you do plane position min equals 1 and plane position max equals 0, like this. And then in the y-axis, you can keep it periodic. There we go. So Aritra got the correct result. I'm going to do it myself now. So the boundary conditions are 0 and 1 for the x-axis, or 1 in the minimum and 1 and 0 in the max. And I'm going to type in that expression there, -1/100 times x plus 1. My simulation size is 256, so if I want to start as a linear gradient, 256 from here. Instead of doing 1 divided by 100, I'm doing 1 divided by 256. Now I can run my simulation. And here it is. That's linear gradient. Linear field. Sorry. Okay. If you already completed this exercise, set a decay constant, and then you will generate the exponential field. So by setting a global decay constant above 1, something like 0.1, 0.01, you achieve the exponential field profile, which is the next exercise. Okay. There is a problem in the chat, mismatched tag. This problem happens, for example, if I don't have this guy here. If I don't have this, I will have that the same problem. So CC2D project, opening player. Invalid token, not well formatted. Not exactly the same bug. Maybe if I copy and paste this somewhere, for example, inside here, I think I can reproduce that. Invalid token, same problem. Uh, Possible solution for our problem is simply copying and pasting. So Nihar, make sure you have exactly the same thing as I have here on the slide. And I'm pasting the boundary for the x-axis, okay? I'll address your problem in the chat, and in the meanwhile, I will move forward. People are already doing the exponential exercise, and I will address your problem there in the chat. So for the exponential field profile, you set a decay coefficient. Right here, if I set a decay coefficient to 0.01, for example, and save, and rerun this, open in player, you'll see that my field is shifting from a linear gradient to something exponential. Of course, I have to zoom in here to see. So maybe if I set a lower decay, And I can set that over here in the model editor in diffusion solver, global. I think it's the second one. If I add a 0 here, press enter, it is slowly going to the right. Let me add another 0. Yeah, it is going to the right, traveling to the right. If I restart the simulation with a lower decay, oh yeah, I can see the isolines moving to the left. Increase a little bit. Yeah. So after waiting a little bit, the field will be an exponential shape. Yeah, this is correct. People sometimes call it logarithmic field. So it's very sharp. Transition is very sharp close to the border, and very low values of the field as you move away from the border. Yeah. Oh, perfect. Working now. Okay. Any problems with this exercise? Just setting a decay makes your field an exponential profile. So if you were to plot the concentration of the field along the x-axis, you would see roughly an exponential shape. Mathematically, truly, this is not an exponential because of the boundary condition. It's something else, but it has a shape that is similar to an exponential. Right? So I think now we are good to go. Let me know in the chat if you need more time. Okay, let's move on. At any time you can type in the chat if you need help and ask me to stop if you need more time. Okay. So to build the exponential field profile, you can set decay, and that's how it becomes an exponential. Why does it become an exponential? So what is decay? Decay is basically removing material from the field at a rate that is proportional to the value of the field everywhere. Gamma is the fraction of the field you're removing per unit of time. Okay. So for example, if gamma is 0.1, you're removing 10% of the field every moment, every time. It comes as a negative term, so minus gamma times C. C is the concentration. And this decay equation is applied in many decay processes, such as radioactive decay, molecule breakdown, so on and so forth. If you solve this differential equation, you get an exponential. That's the solution for that ordinary differential equation. and you will obtain a characteristic decay time that is 1 over gamma. When we have both diffusion and decay, there is another concept, which is the typical reach of the field. The field will diffuse and it will decay like that exponential shape. So it also has a typical propagation range, a typical signal reach. This is very common in problems such as a tumor, where you have nutrient, oxygen, and something else, growth factors in the environment, and they diffuse into the tumor or into the tissue, and you see this exponential profile of the field as you go into the tumor or into the field. That's why vascularization is important, because it allows the nutrients to reach further into the tissue by supplying other places, supplying deeper into the tissue. Not just relying on diffusion, because not only diffusion takes a while to happen, it also the field also gets destroyed but by cells that are absorbing these nutrients, oxygen and others. When you have both diffusion and decay happening simultaneously in a region, the concept of diffusion length is important, and it's given by the square root of the diffusion coefficient divided by gamma. The takeaway from the last lecture is that the higher the diffusion, the faster your signal spreads. The diffusion coefficient will differ from molecule to molecule and from environment to environment. So the same molecule will diffuse at different speeds, let's say, in different fluids, different fluid types. For example, in mucus, we'll have a different diffusion coefficient than in water and in cytoplasm. And in the same environment, such as water, different molecules will have different diffusion coefficients. For example, a virus is much larger than, for example, a protein. So the virus will have a lower diffusion coefficient than a protein. Oxygen is much smaller than a protein, so it will diffuse faster than a protein in the same environment. There are other interpretations to diffusion. There is a geometrical interpretation, and there is a statistical mechanics interpretation, but I will leave those for you to read if you are interested in. I want to remind you before we proceed that diffusion, secretion, and absorption play a critical role in signaling between cells, because a cell will often secrete a signal that the other cell will absorb, and as a consequence, will change the behavior of the absorbing cell. There is a time from the secretion of the signal and the arrival of the signal at this other cell, and they can establish this communication and change their behavior accordingly. So this is often happening in tumor, cell differentiation, tissue development, infection, all sorts of biological phenomena. We are going to explore one very particular one today, two actually. One is the bacterial ecosystem, the other one is the avascular tumor, where diffusion, decay, absorption, production of signals, in this case, they will be nutrient signals. They play critical roles in the behavior of the model, the behavior of the simulation. Secretion, we implement secretion in the diffusion equation enters as a addition term, plus S. S here is a source term. It is something that is added to the field every time and everywhere in space. When we have both secretion and decay, for example, say a tissue that is both producing and eliminating the same substance, like a muscle, when you're working out, it's producing lactic acid, but it's also removing lactic acid. So you have both a source of lactic acid and a decay of lactic acid via whatever removal mechanism. When this is happening, there is another important concept, which is the equilibration concentration. The equilibration concentration is given by S over gamma, where S is the secretion rate or the source rate, and gamma is your decay. If you set up a CompuCell simulation where a blob of cells secretes some field like oxygen, if you have oxygen and you let the cells secrete, it doesn't make sense biologically, but just as a test, if you let them secrete oxygen at a certain rate, and then you set a decay at the same cell type, with the same rate, same value, same numerical value as the secretion rate, the equilibration value will be 1 because it's given by S over gamma. So if they have the same numerical value, the equilibration rate, the equilibration concentration will be 1. And the typical time to reach this equilibration point is the same as the typical decay time, 1 over gamma. Another important concept here. So if you want to reach this equilibration concentration faster, you can increase your decay rate. Of course, if you just increase the decay rate, you also change the equilibration concentration. So you would like to increase both S and gamma to speed up the equilibration and keep the equilibration value the same. Secretion, excretion, and exocytosis and endocytosis, they are different concepts in biology. However, in CompuCell, we are going to use secretion to model any kind of production. So we have a field in the environment and any input, we call it secretion, okay? So if something is producing oxygen, we are going to call it secretion because this is the computational term, the name of the plugin in CompuCell. Okay, although in biology, all these different things have different mechanisms, different they are inherently different between each other. There are many types, many ways you can implement secretion in CompuCell. Many settings, different settings, and they can be very useful depending on your problem, and they can play very important roles as well. For example, you can set secretion by contact. So in this image here on the right, I have these cells and they have a setting that says secrete on contact with medium. So they will secrete just on the boundary between the cells and the medium. While you see this cell here in the middle, the cell in the middle is not secreting anything because it doesn't have contact with the medium. And there are all sorts of different ways a cell can secrete something spatially in the simulation. For example, it can secrete at all pixels. It can secrete just at the center of mass. It can secrete just at the border. It can secrete just at the border but inside, and just at the border but outside the border, into things outside its perimeter. And there are two different ways you can set secretion. One is constant rate and the other is constant value. So this is a little bit like the boundary conditions. If you set a constant rate of secretion, the cell will be pumping field into the simulation all the time. And if you set a constant concentration, the cell will hold the field value at a certain level all the time, no matter what happens. Finally, how do you set secretion? The easiest way nowadays in the modern 4.9 CompuCell is you go to the wizard and you set the secretion rate on a per cell basis in your field wizard page. So in this, the fourth column, you have the secretion rate as the amount per Monte Carlo step per voxel. This is constant secretion rate, which means the cell will be pumping material into the field all the time. And the second version is the constant concentration. So in this case, the cell will be holding the field concentration at a certain level. The next column is secretion on contact. So this is conditional secretion when the cell has contact with another cell type. And here you will list the cell types that you allow contact. For example, medium, comma, space, cell B, comma, space, cell B, cell C, etc. You can set uptake. So uptake is absorption. I'm going to touch on how it works in a minute. But uptake, there are two parameters. One is the max uptake rate. So your cell will be extracting material from the field, and the max uptake is the maximum amount of field your cell can uptake per time, per period of time. And the relative uptake is if the concentration of the field is below this maximum threshold, it's going to make the field decay with this relative uptake rate. It's a relative uptake, so it's a percentage of the field. So for example, if you set relative uptake 0.1, you will be consuming 10% of the field material locally in the cell every Monte Carlo step and everywhere in the cell on all pixels of the cell. All these settings will show in the XML if you activate them. So you'll see something like secretion data. If you set an uptake, there will be an uptake line with a maximum uptake parameter, the relative uptake parameter, and the cell type. The secretion on contact, if you have, there will be a list with cell types for the conditional secretion and the cell type that secretes it. You can also call a secretion plugin from the CC3D ML menu if you don't have secretion in your current simulation. So you go to CC3D ML and then plugins and hit secretion. Just make sure your cursor is not inside another block. So for example, if my cursor is here inside the center of mass and I invoke that plugin, it's going to crash my simulation. My simulation will not run. I have to place my cursor outside any pre-existing blocks. You can also set up secretion via Python. In this case, you will hit. Oh, oh, I think let me. Yeah. So sorry for this. There is a missing slide. If you want to control secretion in Python, you have to hit a setting in the wizard. Let me get there real quick. There is this setting here, control secretion through Python. If you want to control secretion through Python and you are setting up your simulation in wizard, you activate this this little box here. Okay. Why would you do that? Why would you give up on the very convenient wizard field setup? There are many reasons, but they might not come soon enough for you during the hackathon. So for example, if you want individual cells to secrete, so they have the same type, but one particular cell of that type wants to secrete because it's at a certain position, or if you want to set conditional secretion based on the state of the cell or some event that happens. For example, I just want the cell to secrete after Monte Carlo step 100, right? So if there is an event or a process, something that is happening that is causing the cell to secrete. Also, if you want to programmatic control of the field, for example, one example of programmatically controlling the field is if you're optimizing your simulation. You can manipulate all the parameters and how the cell secretes things. For example, let's say you want to toggle between many modes of secretion automatically from another script. You will use Python implementation for this. And there are other use cases. For example, tracking the amount secreted by a cell, the amount of field taken up by a cell, and many other options. Here's a link for the documentation if you're interested in seeing how you set up it in Python instead of XML. If you have it on Python, you can also get the total field integral if you want to have some creative simulation outputs. The amount seen by a cell, if you want to let the concentration at the cell influence the behavior of a cell, and track the total amount secreted or taken up by a cell. So these are all things that you can do in Python and you cannot do in XML. For uptake and endocytosis, so again, same idea, you are removing material from the field. So we will model all those removal mechanisms. We will name all of them uptake because that's the name of the plugin. It's uptake. Okay. For uptake, the cells will behave as either sinks or decay places, places where the field will reduce in amount. Okay. And there are two parameters, the maximum absorption rate and the relative absorption rate. This is how it works. Below a threshold, below a saturation threshold, your cell will take up an amount that is proportional to the field concentration locally. And above this amount, there will be a maximum uptake rate. So this is, for example, let's say you have a metabolite like glucose on the simulation. And biologically, if there is a lot of glucose, like too much glucose, the cell cannot take up everything. So there is a saturation threshold for that. Uptake is automatically implemented in your simulation when you invoke the secretion plugin. So there is no such thing as an uptake plugin. In the secretion plugin, you already have access to both. When you track, this is a note, when you track the total amount taken up by a cell, you will see a negative value because it's removing material from the field, and the total amount takes into consideration gain or loss of the field from the perspective of the field, not from the perspective of the cell. So when you ask the cell how much field it has taken, it's going to say minus something because it's removing material from the field. And if you're asking if the cell is secreting something and you ask total amount, it's going to give you a positive value. For our next exercise, we are going to build, we'll have two cell types. They are frozen, they are not moving, one on the left and one on the right. One cell is secreting a field and the other cell is absorbing it. So this is the most basic setup of cell communication via signals, where you have one cell somewhere secreting something. This signal spreads through space, takes a while to reach the other cell, and the other cell consumes it. Not only it consumes it, it leaves a shade behind. So if you had another cell behind, it would see a lower concentration of this field because there is another cell in front of it taking it up. And these are the steps. So first thing you will do is to create a simulation with two cell types, and you will select control secretion via Python. Yeah, so here we're already giving up on the XML. You can use the wizard. That's no problem. You don't need to use Python here, because XML already provides everything you need for this particular exercise. But if you want to practice the pure Python implementation of secretion, then you say control secretion via Python. And then if you do that, this piece of code will be relevant for the exercise. The first line is getting the field object, and then for cell in the cell list by type CellA, you do a secretion, and for cell in cells in cells of type B, you do an uptake. Of course, since you just have one cell, it doesn't you don't exactly need to do a loop, but that's an easy way just to acquire the cell object anyways. So question, is there a difference between pure Python in Twedit and pure Python in VS Code? So this question is basically if I come here to my steppables.py, all the Python code I have here, is it going to be any different if I am using a VS Code pure Python without XML, without any player, without any to edit? I just have one Python script. Is the syntax different? No, it's the same syntax. If I want to create a new simulation file all over, do I have to use the wizard? No, you do not have to use the wizard. You can start demo, from a demonstration code. How to do it directly via Python? In Python, what I do is I start from a pure Python demo that you can access, for example, on GitHub. Then I copy and paste on my Python file and add it on VS Code, for example. But maybe I misunderstood the question. If you want to create a simulation file that contains XML, contains the Python master file, contains the steppables file, all separate, all organized, compatible with Twedit, compatible with Player, I suggest you use Twedit for that, using the wizard. That's my suggestion. All right, so I'm going to start the exercise myself now. So if you got stuck, you can watch me doing the exercise, or you can just use the time I'm using to do the exercise to finish it yourself. And if you are done with the exercise, please, you can feel free to share screenshots of your simulation in the chat. So I'm gonna build a simulation right now, CC3D project, new CC3D project. I bet you guys are familiar with this already. I don't really care about this page. Yeah, I'm going to define two cell types, cell A and cell B. I can freeze them, or I can just freeze them. Just easy. Next. Next. Then I have a field. I'm gonna call it field like this. This is my field. Here I'm going to set control through Python. And I'm going to set the boundary conditions as, that's fine. Constant derivative 0. If I want to have decay happening only on the cells with uptake, I'm going to set decay coefficients 0 here on global and on cell A. and on cell B too. And the next, and finish. Here, show project panel. There we go. So this is my new simulation. And it has like a standalone secretion thing here with nothing in it. And now I'm going to implement what we have in the slides. So I'm going to drag this to the side. So, and now I'm going to reproduce what I have on the slide. So I want to take my field secretor, the secretor object, so I can invoke it and say cell secrete this amount. But instead of just copying from the slide, I'm going to show you how I will do this if I didn't have this code. So if I didn't have this code, I would go to CC3D Python. I would go to secretion uptake. I would go to secrete inside cell. And I get these two lines of code here. The first line of code that I got, secretor equals na 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 na. This is the secretor object. I have to give it the field name. So it has to be the same name of my diffusion solver field name. So that goes here. Exactly the same name. And the second line tells the cell to secrete it. But I don't have a cell object. If I just run this, it's going to crash because I don't have a cell. So I have to loop over cells. And to get to the loop, because I'm not copying from the slide, I will go to CC3D Python, visit, and visit cells of a given type. This is giving me this code. There is a loop, self.cellList by type, na, 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 na. I'm going to bring the secretor secrete inside cell into this loop. And I'll make this loop be over cells of type CellA. So types of cells of type CellA, all uppercase, okay? All uppercase letters for the cell type. And as in the slide, for the secrete inside cell on cell A, the secretion coefficient is 0.1. And I'll have something similar for cell B. So instead of cell A, I'm looping over cell B. And instead of secreting, I'm taking up. So Python, secretion uptake, and I'm doing uptake inside cell. It gives me a bunch of syntax. The first line of code is redundant. I already have it, so I'm going to delete it, which leaves me with just uptake inside cell. And here I'm going to set a max uptake of 10, as it is in the slide, and a relative uptake of 0.1. Oh, those are very nice results. Very, very nice results. Perfect. Okay. And they should be good to go. Let me run. And if it doesn't crash, what a miracle. Oh yeah, nice. So it's not crashing. And if I see my field, oh, that's interesting. Does this make sense? Does this make any sense? Yeah. I have the cells of type A, which are the red cells, are secreting, and the cells of type B are absorbing. But I don't have my two cells, one on the left and one on the right. I have this initial random configuration. So to change that, I'm going to the XML, and I'm going to separate this region into two. And I'm going to create just cell A on the first region and just cell B on the other region. For the first cell, cell A on the left, I will be creating from 20 to 30 and from 20 to 30. And for the other one, I'm going to create from 60 to 80 and from 60 to 80. So they are far away from each other. And I have to give it a width that is the same as the box size. And I should have just one cell. Now, if I rerun my simulation, oh, I'm creating 4 cells over there. Oh yeah, so from 70 to 80, from 70 to 80. That's my mistake. All right, so now I have 2 cells. Cell A is on the bottom left, cell B is on the upper right. And if I let this run, oh, it's taking a long, long, long time, right? So how can I speed this up? I can increase the diffusion coefficient, right? So if I come here to diffusion and I set the global diffusion to something like 1 and press enter, it has to be a float, 1.0. Then it diffuses very, very fast. And I can more quickly get to the result I'm looking for. So I can already see the shade happening. Not quite colorful as the other one. Oh, there we go. So I just increased the diffusion everywhere, also inside the cells, and I very quickly achieved the colorful um, output here. This shouldn't be read-only. No, you double click the value, you type in a float 1.0 and you press enter. Are the model editor properties read-only? No. So double click, set a value, press enter. The advantage of doing this, instead of using XML, is that instead of typing a 0.1, this can be a function of something. This could be a function of x, sine of x, right? This can be anything. It can be a real function of something. It can be dependent on time, dependent on anything you can imagine, okay? So you have complete freedom in Python to do whatever you want. And you can also change all these parameters from the outside. For example, if you're doing model fitting to data, or if you're calibrating your simulation, or doing a sensitivity analysis, doing Bayesian inference. So it's less accessible, it is harder, but it's more powerful. What should be the initial concentration for this case? It doesn't matter. The initial concentration doesn't affect the end result. So even if I set an initial concentration, I went there and I set my initial concentration to 100, and it looks like this. And even in this case, if I press run, eventually it reaches the same pattern. And if you are unable to see your field, is because you are looking at the cell field over here. But then you hit this drop down menu and you select your field visualization, and then you should be able to see it. So from now on, eventually leading to the hackathon, we are going to start thinking about how to build a model. And there are some relevant philosophical concepts that helps you to think about building a model. Because oftentimes you start coding before you thought deeply about the problem, and then you find, for example, that your model isn't useful or that your model doesn't represent a real problem. And that's critical because a model, if it's not useful, it's a bad model. It's not something you can publish, it's not something you can use to make predictions, etc. So let's start from the start. What is a model? A model is usually defined as an imitation, a representation, or an approximation of some real-life system. Or something that you imagine. It could be something from your imagination. So for example, you could imagine a new model of airplane, a new type of airplane, and then you go to your modeling tool, your simulation, and you build a simulation out of it. Okay? You could be imagining a circuit, or you could be imagining a new building, and you build a model of it, even though it doesn't exist in real life. Why do we build models? We build models because we are testing hypotheses or perturbations to systems, making predictions, or identifying critical missing information in a way that is cheap, fast, and low risk. So for example, imagine I want to explode an airplane and ask if it's going to fly after I do that. If I do it in real life, I will lose the airplane, but I can safely do so in the simulation. Okay? So silly example, but that's kind of true. Especially in biology, where you want to overdose your cells with a toxin, doing that in real life is expensive, and if you can even model the whole organism and fill it with toxins in a simulation without any ethical complications. Okay? So there are also ethical problems associated with doing things in real life rather than in a simulation. So a philosophical question here is, should you ever trust a model? Why should you? Why would you not trust a model? When would you? When you wouldn't? Should you trust a model? Yes or no? Identify its limitations. Caution. You could fail to incorporate relevant data. You can trust a model if it's validated. Yes, if it can replicate the experimental data with right inputs. It depends on how well it has been parameterized or constructed. All models are bad, but some are useful. Yes, maybe, after validating with experimental values. Okay. Not fully, because it doesn't account for all external variables of real model, variables are real model would. Okay. From a Bayesian perspective, it depends on how much evidence there is to justify the power of your belief in a model's output. There is also the concept of reduced chi-squared that tries to answer this precise question, how much data you have versus how simple your model is. Also, it's kind of a derivation of the Occam's razor principle. Also, how much risk you're willing to take, which depends on how much evidence the model has. And it also depends on what are the stakes, right? If I have a model of a patient that I'm using to calculate how much drug I'm going to inject, I will be more cautious than if I have a model of a cell phone or like something less like risky, you know? It's subjective. Totally depends on the type of system you're modeling and whether the required parameters are included and validated or not. So my personal answer is no, never. Okay, but that's a long discussion. So cautiously, yeah. Let's never say we trust a model. Okay, let's agree on that. Let's never say that. Let's always be careful. Before you build a model, there are some things you should think about. And if you list them and think about them clearly, especially writing them down, it's going to be easier to build your model. It's going to be more tied to biology, more tied to real world, and less just like a toy model or like something you're playing with. Okay. So the first thing is the biological observations. Qualitative or quantitative data from experiments. They depend on the experimental setup and might conflict with other sources of data. For example, the concentration of a signaling molecule. There are also assumptions, processes, events, and interactions that you expect are present in the system and are relevant to your model even though they are not reported in the biological observations. For example, cell metabolism. If I'm watching a cell in the microscope, I am not seeing the citric acid cycle, but I might assume it is present. Okay, it's a very reasonable assumption if my cells are of a certain type, of a certain animal. Okay. Mechanistic hypotheses. What are mechanistic hypotheses? They are basically a reason to an observation. So why am I seeing what I'm seeing, and I'm giving it a reason. And this reason is derived from an understanding of the underlying biological mechanisms. For example, uh, I think the tooth cavity comes from pH, pH being too high. So there is a mechanism. pH is degrading a certain tissue, and that eventually creates a cavity. This is a mechanistic hypothesis. Another example is nutrient deprivation limits tumor size. This is a very common mechanistic hypothesis when we're studying tumors. And there are scientific questions. They are questions about the observations or the mechanistic hypothesis that you can answer with your model. So this is key. These are questions that you can address with your model and the observations. You can very well ask questions that are not answerable with your model. For example, why does a cell exist? That's not a scientific question. An example of a scientific question is mechanical pressure from the surrounding tissue enough to limit tumor size? This is something you can build a simulation, you can test, right? Once you think about these things, you are more prepared to build your model. And the model has a structure. It contains objects. Objects are the carriers, or the typo here. They are the carriers of behaviors. For example, cells, the environment, the walls of the environment. A field is an object. For example, an oxygen field. Processes are actions that play out in time, like growth, movement. Events are actions that happen at an instant, like division, death. Behaviors are processes and events that an object possesses, like movement, death. Interactions necessitate more than one object exchanging information. For example, repulsion, adhesion, they necessitate more than one object to take place. Dynamics are the rules that govern how these processes and events take place in space and time. For example, Newtonian dynamics, the diffusion equation that we saw, Celer-Potts model. They are the orchestrators of the system. And you have also the initial and boundary conditions. How the objects are displaced initially, how they interact with the boundaries. For example, in our previous example, we had this case here. What are the objects, interactions, behaviors, and dynamics? So for dynamics, we have Celer-Potts model, we have isotropic diffusion over a chemical, we have a constant rate secretion. These are telling us how things play out in space and time. We have our objects. They are the medium, the cell, CellA, CellB, the field. I could also say the domain, the lattice. I can also consider the lattice as an object of this model. So this field, this concentration field. And I have interactions. So interactions take more than one object. For example, cell A and field, they are interacting by having cell A secreting the field. Cell B is interacting with the field by absorbing it. And a behavior could be, for example, the cells are sitting still. That's a behavior. They're sitting there. They don't move. The field diffuses. That's a behavior of the field. Okay. Now let's apply this to a more complicated model. So in this model here, and I'm going to ask you to uh, provide the answers in the chat. We have two types of bacteria in a petri dish. We observe that both bacteria proliferate and die. This is an observation from a microscope, whatever. And we observe spatial patterns emerging on the petri dish. Let's make one assumption. Let's assume that one of the bacterium type, is getting all its energy. We're also assuming they have metabolism, but I'm not saying it because it's kind of obvious. Well, let's assume one bacterium is getting its energy from nutrients in the medium, nutrients that are present in the medium. Let's assume that the other bacterium is getting its energy by consuming the waste product of the other bacterium. Now let's come up with a hypothesis. Let's hypothesize that the spatial pattern we observe, I'm not telling you what the pattern is because that's a spoiler. Once you build the simulation, you'll see it. Let's hypothesize that this pattern emerges solely from the metabolic behavior of both the bacteria. So not from adhesion. That's a hypothesis. I don't need adhesion to get this spatial pattern. If I just mess with the metabolism of the bacteria, I can recover the pattern I observe experimentally. So this is something I can test. I build a simulation, I see if it recovers the pattern. If it doesn't, my hypothesis has one counter evidence. Okay? So this is the setup, this is the problem, and that's the answer. I want you to provide the model structure for this. What are the objects, behaviors, interactions of these objects? Okay. So that's the exercise. Okay, we have an answer from the chat. The model should account for two types of bacteria. For both, there should be mitosis and death. Bacteria A absorbs nutrient via diffusion, and it secretes something that is taken up by bacteria B. So we should have a diffusion solver with secretion coupled with bacteria, mitosis, and death for both A and B. Boundary conditions, no flux at the edges. Another answer. Objects. Bacteria A, bacteria B waste a medium nutrient. Okay. Interactions. Medium provides nutrients. Okay. Bacteria A gets those nutrients. Bacteria A produces waste. Bacteria B uses waste. Behaviors. Bacteria grow and divide. Bacteria dies out. Behaviors. Field diffuses. That's an important behavior. Bacteria grow and die. Also divides. So it's interesting to see that some actions, objects, behaviors, interactions, some people forget to include, some people remember to include. Dynamics. Isotropic diffusion, proliferation is important. Grow or divide as it consumes field 1 while secreting field 2. Bacteria B starts to grow. Size of bacteria A is balanced between absorbing and secreting until it runs out of nutrient and starts to shrink. Interesting ideas. Okay, let me give you my version. Okay. Doesn't mean it's correct. Everything here is up for debate. This is my version. I have medium, bacteria A, bacteria B, nutrient, and waste. And I have the interaction. So medium replenishes nutrient, bacteria A consumes nutrient, bacteria A releases waste, bacteria B consumes waste and does not consume nutrient. This is just a reminder. And there is zero surface tension between all cells. So I am explicitly stating that there is no adhesion, not necessary. Cells can grow and divide based on their access to the food. Cells divide when they can't access food. So cells die when they can't access food. And waste and nutrient diffuse and decay. And the homework is building pseudocode for this model, okay? Which is how you would implement it in CompuCell. What is pseudocode? Is a very simplified spoken language for algorithms. So for example, loop over cells of type A, cell secretes waste, cell absorbs nutrient. If energy falls below threshold, the cell dies. And you can download the simulation and it looks like this. So this is already a spoiler of an implementation of that simulation in CompuCell. And you see how it can recover a spatial pattern, namely a cell segregation pattern, although I don't have any differential adhesion mechanism in the simulation. It's just based on metabolism. The cell that consumes nutrient from the medium tends to stay on the outside, and the cell consuming waste tends to be on the inside. I was supposed to be showing this.